This chapter is a brief introduction to chemical equilibrium. Many reactions that we carry out in the laboratory are actually reversible. While we treat many of them as if they go only in the forward direction, many of them reverse to a fairly significant amount. So now we're simply going to be calculating how much of each substance there is when the reaction reaches equilibrium. This really is nothing more than just a little bit of fancy stoichiometry. When you look at a graph of concentration versus time, over time, the reactants will decrease their concentration over time as they turn into products. The products will increase their concentration over time as they become reactants. At equilibrium, the concentration of the reactants and products no longer changes. They are not equivalent to each other, but they are no longer changing. That is the point at which you have reached equilibrium. When you look at reaction rate versus time for an equilibrium reaction, the forward rate decreases as you use up reactants. And the reverse rate speeds up as you increase the reverse reaction by turning products back into reactants. You've reached equilibrium when the forward rate equals the reverse rate. What conditions do you need to reach equilibrium? Well, you need to remain at a constant temperature so that you don't change the kinetics of the reaction. You need constant pressure, and for gases, you need a closed system. What's equal at equilibrium? Well, rates are equal, but concentrations are not. The concentrations are no longer changing. They are not necessarily equal. Equilibrium means forward and reverse rates are equivalent, not concentrations. Le Chatelier developed a very nice, simple, qualitative, and it can be turned into quantitative as we move through the chapter, prediction of how to determine what will happen to a reaction that's at equilibrium when you upset that equilibrium situation. He says, if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that reduces that change. So a system that's equilibrium is changed, then it's going to try to undo that change and reestablish equilibrium. So the simplest way to look at Le Chatelier's principle is to look at changing the amounts or concentrations of reactants and products. So you can add a product, remove a reactant, add a reactant, remove a product. Each of these will have a change on the equilibrium position. If you add a product, then the reaction is going to shift to try to undo what you have done. So it's going to shift to the left to use up that product. If you remove a reactant, the reaction will try to undo what you just did. If you remove a reactant, it's going to shift to the left to try to make more of that reactant. It's trying to undo the change that you did. Adding a reactant will shift away towards the product side. The equilibrium will shift to the right to try to use up that added reactant. And if you remove a product, your reaction will shift to the right to try to use up that product, or to try to, make more of that product that you are removing. So this will keep the reaction moving towards the right. If you change pressure, you're looking at gases, so one of the ways to change your pressure is to change the container volume. So if you decrease the container volume, your volume goes down, your pressure will go up. The stress that you've put on the equilibrium system is that increasing pressure. So it will shift to try to decrease that pressure, which means it will shift in the direction where there are fewer moles of gas. In this case, that would be to the right, where there are 3 moles of A2B3 rather than the 6 moles of A on the left. If you increase the container volume, volume goes up, pressure drops. So now the reaction will shift to try to increase that pressure. So now it will shift towards the left where there are more moles of gas. Remember, only gas molecules can be affected by the pressure, or only actually, it's better said, that the changes in pressure will only affect the gas molecules, and only the gas molecules can affect the changes in pressure. If you happen to add an inert gas, or a gas that's not part of the chemical reaction, you're not going to affect the equilibrium at all. The partial pressures of the reactants and products will not change. They're not interacting with this new gas. The total pressure changes, but the partial pressures don't change, so there is no shift or change in the equilibrium position. Changing temperature affects a lot of things about the reaction. First, it will change the kinetics. It will affect both the rate of the forward and reverse reactions. So it doesn't just change the equilibrium, it changes the kinetics as well. So when you're looking at the shift based on temperature, you're looking at whether the reaction is exo or endothermic. An endothermic reaction, where heat is a reactant, if you increase that, think of heat as a reactant, and think what we did when we added more reactant. If you increase that heat, the reaction is going to shift to use that heat up. So it's going to shift to the right to produce more product. If you have an endothermic reaction and you decrease the temperature, that's like removing the heat. So the reaction is going to shift to the left to try to make more of that heat. In an exothermic reaction, where heat is a product, increasing the temperature would shift the reaction to the left. You've increased some of that product. You're going to shift to the left to use it up. Decreasing the temperature would be removing some of that product, so you're going to shift to the right to create more heat. Think back to your thermodynamics, where your exothermic reactions are always more favorable under lower temperature conditions, and this is supported by the fact that with Le Chatelier's principle, if you remove heat, you shift the reaction to the product, more favorable, more negative delta G side of the equation. So if we look at this reaction and we were to add more N2O4, you're adding a reactant that's going to shift to the right to use it up. Adding NO2 is adding a product, shift to the left to use it up. Removing N2O4 shifts to the left to make some more. Removing NO2 shifts to the right to try to make some more. Adding helium will not change the equilibrium. Decreasing the container volume would increase your pressure. Your pressure would go up, so you would shift to the fewer moles of gas to the left. Increasing the container volume, shift to more moles of gas to the right. And since this is an endothermic reaction, increasing the temperature would shift the reaction to the right. The law of mass action, notice this is a law, not a theory. You have a balanced equation. You have your JK, which are your coefficients. So the law of mass action says K, and the equilibrium constant is an uppercase K, is equal to the products raised to the power of their coefficients over the reactants raised to the power of their coefficients. You do not need to find those coefficients experimentally like you did with kinetics. These are very simply based on their mole ratios. Remember your brackets again meaning molar concentration or molarity. If you know K, then you can predict the concentrations of products and reactants, and if you know the concentrations, you can find K. So this is the equation we'll be working with throughout all of our equilibrium problems. This is called the equilibrium expression. When you're relating small k and capital K, small k, of course, is your kinetics K, and big K is your equilibrium K, and you must make sure that you write those correctly on your exam. So if the rate forward is equal to the rate reverse at equilibrium, then K forward is equal to K reverse at equilibrium, and your equilibrium K is a ratio of K forward to K reverse. When you're using molarity, you often see many different expressions for K. It can be the simple K, KEQ, or KC for equilibrium and concentration. If you're using pressure, then it is called KP. When you're looking at equilibrium that involves solids or other states of matter besides gases and aqueous, you have to think about the concentration of a solid. Remember, your K expression is your molarity, always molarity, and gases can have molarity based on their moles and their volume, just like aqueous solutions. But pure solids and liquids do not have a concentration. They have no molarity. Their concentration cannot change. Therefore, you do not write them in the equilibrium expression. They have no effect on the equilibrium position. That seems a little confusing if you look at the equation above, solid calcium carbonate decomposing to solid calcium oxide and CO2, the equilibrium expression would include only the CO2. But even though the concentrations of the calcium carbonate and calcium oxide are not included, they do participate in the reaction and must be there for equilibrium to be established. But changing them will not change the equilibrium. When you're looking at the size of K, you're looking at whether you have a product or a reactant favored equation. So if you have a large number of products, so your reaction has equilibrium that lies to the right, it is product favored, it has a K greater than 1. At equilibrium, you have mostly products. If you have very few products at equilibrium and mostly still reactants, then you're a reactant favored, or equilibrium lies to the left and K is less than 1, meaning at equilibrium you have mostly reactants still. You have not gone very far forward in your reaction. There are no units for K that we write. If you think about the molarities and the powers of the coefficients, these get really complicated. So K units are not usually written. Just need to make sure that you write an uppercase K for equilibrium and lowercase for kinetics. Playing with K. By playing, we mean using it in a situation similar to Hess's law, where you are finding the K of a reverse reaction or something where you have multiples of the coefficient. When you write a reaction in reverse, you don't take the negative of it, you take the inverse of it. So if you reverse the K or inverse the reaction, the K is inverse. And if you multiply the equation by some constant, you don't multiply the K by that, you raise it to that power. So, for example, if you had two reactions that you were adding up, similar to Hess's law adding up heat, and you want to find the K for that reaction, and you have the K for each reaction, you would do what you needed to do to get the reactions to add up to your net equation, and then instead of adding your Ks, you would multiply them to get the K for that reaction. When you're talking about Kp, Kp is simply the equilibrium constant with respect to pressure. So if you're using all gases, what you have found is Kp instead of just Keq or Kc. You used to have to know how to convert between K and Kp. They were giving you an equation that told you that Kp was equivalent to K multiplied by the gas law constant RT, and then raised to the power of the change in moles of gases. You no longer need to do this, but you still need to know that if the change in moles of gases if there is no change in moles of gas, let's say, then you have K being equivalent to Kp. So while they don't expect you to have memorized these equations and you don't have to use them, for some reason you still have to know that when the change in moles of a gas is 0 in going from reactants to products, then your K value and your Kp are equivalent to each other. Anything, of course, raised to the 0 powers 1, and that's what makes them equivalent. The reaction quotient, Q, is simply the same math as finding K, but it's telling you where you are in the reaction prior to reaching the equilibrium concentrations. So it's going to tell you the direction in which the reaction is going to need to shift in order to reach equilibrium. So now you're putting these into still Q is equal to products raised to the power of the coefficients over reactants raised to their power, but notice the little subscript 0 there, meaning the initial concentrations. So you can calculate Q and compare it to K to determine which direction your reaction is going to go in order to reach equilibrium. So if Q, when you calculate it, ends up being less than K, then that means initially you don't have enough products. So your reaction is going to shift to the right to make more products. So remember, the math for Q and K is the same, products over reactants. So if Q is less than K, you don't have enough products, you're going to shift to the right to make more products and establish equilibrium. If Q is greater than K, it means right now you have too many products initially. So now you're going to shift to the left to use up those excess products and reestablish equilibrium. Equilibrium is established when you have a specific ratio of reactants to products at a given temperature. So if your K is greater or less than that, then you're going to shift in a direction to create that equilibrium position. If Q is equivalent to K, then your system is already at equilibrium. So, for example, if we have this reaction and we know the K value, and notice products over reactants raised to the power of their coefficients, and K is 5.10, K being greater than 1, not much greater, but greater than 1 tells us when we're done, we'll have mostly products in this reaction. So initially, we have 1 mole of each gaseous substance in a 1 liter container. Which direction are we going to go to reach equilibrium? So first we calculate the molarity of each component. 1 mole over 1 liter makes it 1 molar for all of them. Then we're going to calculate Q, since these are initial concentrations. Okay, put in 1 times 1 divided by 1 times 1, so we get a Q value of 1. Since Q is less than K, right now we're going to shift the reaction to the right to create more products, which is what our K indicated we would be doing since it was greater than 1. There's a connection between free energy and equilibrium, and it's an equation that's provided on the exam. It's plug and chug. You have to understand some conceptual things, and you have to be able to use it. We know that K is the equilibrium constant, and delta G and Q are provided. And at equilibrium, we know that delta G is equal to 0, and Q is equal to K. These are important conceptual understandings. So a negative delta G is a thermodynamically favored process, meaning product favored, meaning a K greater than 1. Delta G equals 0 is an equilibrium situation where K is equal to 1. And a positive delta G is non-thermodynamically favored, meaning that you do not favor products, you favor reactants, and your K less than 1 indicates reactant favored. So your connection between delta G and K conceptually is very important. To use the equation, you might be given a set of data where you have a delta H given to you and an S value. So you're trying to solve for the K for this. So you're going to use your thermodynamic data. You're going to plug in first and find your delta H. And in this case, they've turned it to joules to relate to the same unit as the S. Remember, your delta H and your S units and your delta G units do not always agree. So you must make your unit agree. Then solving for delta G by using your delta H and T delta S. You get a negative delta G there, which indicates thermodynamically favored, so we should predict a fairly large K value here. It's a quite large negative delta G. Plugging into the equation, delta G is equal to negative RT ln K. Notice the R that's used is the 8.314, which uses units of joules per mole Kelvin. So not your 0.0821, but your 8.314 R value, which is provided on the exam as well. And then solving. Now this K, e to the 601st power, many calculators cannot give a value that large, and mine could not, so it's perfectly fine to write K is equal to e to the 601, but we'll practice some of these. So this is your first introduction to equilibrium. Most of it is pretty qualitative, and then as we move forward in the chapter, we'll get into the quantitative aspects.